Possible outcomes at the same time, all the possible values at the same time. So suppose you want to evaluate f of x for x equal to 0, 1, 2 up to say 100. You want to evaluate f of x. So classically, if I wanted to evaluate f of x, what you will do? I will go and compute f of 0, compute f of 1, compute f of 2, compute f of 3, and up to f of 100. So I will try to compute all those things. But in quantum computing, so if you can create a particular state called a superposed state, which is summation over I varies from 1 to 0 to 100 in this case, and with the scalar factor, 1 by root of 1 not 1, some scalar factor comes in. For time being, we don't worry about the scalar factor now, but the whole point is it's superposition of all these states. Now, if we pass these states into a system which computes f of x, which means I can compute f of 0, f of 1, f of 2, up to f of 100 at the same time, which means it supports enormous amount of parallel processing. The only challenge is that parallel processing and other kind of application for quantum quantum information is security. So you have certain kind of states like so there's one phenomena called if you measure the quantum state, it will disturb the quantum state completely. So which means you cannot retract, like the information loss can be detected from the transmitter and sender. So if a third party try to read the data in between, he cannot read the data without corrupting the data. The data gets corrupted. So the receiver, when he receives this corrupted data, he can identify that someone has interfered with the data that is being transmitted. So it can be identified. So it helps in security and confidentiality. Okay. And now why should we do research? Now it supports parallel processing, it looks nice, but we have to do research in quantum algorithms or quantum computers related problems because there are some challenges too. The first foremost challenge is no cloning theory. So classically, if you have a hard drive, you can copy the information in another hard drive or in another pen drive or in a system in a system's memory. You can store all this information in different memories. You can copy the data, whatever you have, you can copy the data and put it on another thing. But this quantum information cannot be copied. Pure quantum information cannot be copied. That is the first challenge. So you have to develop algorithms nicely so that the copying does not affect the nature of the results that you are expecting. Okay. And second challenge is reading the data corrupts the data. So though you compute f of 0, f of 1, f of 2, f of 3 up to f of 100. Now if you try to read the result, you try to find say f of 0, you wanted to find f of 0, you put a measurement device and try to read the value f of x, and then the resultant will not be like you will not get f of 0 to f of 100 at the same time. You cannot read it back. The system will compute it and it will store there. But if you try to read it, you will either read f of 0 or f of 1 or f of, you will read only one of that. You can't read everything together. So that is a challenge here. So the other problem is once you read it, it disturbs the state of the system. Like once you read f of 1, the information about f of 0 up to f of 100, except f of 1 gets erased. So you cannot get it back. Again, if you want to compute f of 1, again you have to go back to the algorithm. Again, it looks like a classical machine. Like you read f of 0 first and then go to adjust the structure of this problem depending on the problem. Soon we will see some examples, and then we can nicely improve the speed than the classical speed. And other thing is, all classical algorithm are not a good quantum algorithm. So you can convert every classical algorithm into a quantum algorithm just by encoding the classical information into a special type of quantum information, like what I did here. Here I map zero here into the state. So you can encode the classical information into a quantum information and convert every classical algorithm into a quantum algorithm. But then that will not be efficient. Not all quantum algorithms are efficient. Not all algorithms are efficient. So some of them may work on par with the classical algorithm. So if you want efficiency, if you want the speed, the computation to be faster, then your algorithm should be designed to the quantum systems. It should be designed appropriately. And the last most challenge in quantum computers is noise. So classical computers, if people from classical communication are there, people might have learned this error correction code for a long time. And we are matured enough that classically computers, we don't worry about noise these days. We just type the information and say that information is secure there. It's 100% secure. We don't even think that there is some noise, though there is noise which is handled by error correction codes or the other techniques that is involved in the internally in the hardware. But quantum computers, they are in the infancy stage. Like, so this error correction, so we need so our quantum computers, those are being developed now, are noisy. So they have different versions of noise which we have to study, and we have to protect our information from all these noises. So we have to do research on all these directions. Okay. And next, I will try to introduce quantum information from a coin toss perspective. So this is one of my own intuition. So suppose you toss a coin and it lies on the floor, and the resultant will be heads or tails. Here in this case, to give it a pictorial representation, we have given green or yellow. Okay. So you will see either heads or tails. So you toss the coin, you will see heads or tails. The coin is on the floor, you will see heads or tails, which is exactly the classical bits. So you know what is it, heads or tails. Heads means 0 and tails means 1. Okay, fine. And then I wanted to add few things. I wanted to add something called as reference plane. For classical information, the reference plane is the floor itself, the same floor itself. Okay, that is the place where the coin is being lying. The plane which differentiates 0 and 1. Okay. And now I wanted to tweak the coin little bit. I wanted to allow the coin to stand also. So now say for example my coin stands like this. Now a person seeing from the left hand side will see the coin as heads, and seeing in the right hand side you will see the coin as tails. So both of them see different sides of the coin. So to tackle that, so we will do is we will introduce something called as observation sphere. It is a small sphere that we keep it uh, above this plane. So we will keep it above this plane. We will keep this sphere above it. Okay, and we will ask the observer or the person who is going to see the coin to pick a point on this hemisphere and choose one point in the sphere and observe the coin. So the observer can see heads or tails. Yeah, any questions? Okay. So for example, if the coin is like this, I pick the coin. If the observer somehow stands here and sees the coin, he will see green. If the observer is standing here, he will see a yellow. So the coin, the outcome of the coin changes depending on the position of the observer. So if the observer is standing here, he will see green. If the observer is standing here, he will see yellow. So the outcome changes depending on the position of the observer. Okay, and we call this probability. So green with the probability 0.5 and yellow with the probability 0.5. And if the coin is standing like this, then he will see green with the probability something less than 0.5 and yellow with the probability something greater than 0.5. So the outcome changes. Okay. And classically, these can be represented by a small vector. And normal notation will be like P and 1 minus P. So to give a connection between classical and quantum information, instead of P and 1 minus P, I will give root P and root of 1 minus P. I will denote it with this. And it's a one-to-one notation comparison, so it's fine. There's no issues in placing root p instead of p. So classical randomness we represent by root vector, which is denoted by root p and root of 1. Yes. Any questions? So I heard some audio. Is there any questions? Okay. So if there are no questions, then I will try to continue. Okay. So now what so now if you see, you can see classical randomness. So if my coin is like this position and this position, both will give me the same randomness. The coin is on one side, and here also there are many places over which the distribution of P and the green and yellow remains the same. If the coin is like this, the probability of green is this area, and if the coin is like this, the probability of green is this area. And these two are almost same. You can visually see it. And if the coin is facing front, tilted in the same angle, then again the region over which you see green remains the same. They don't change as long as your coin is the angle of the coin with respect to the ground, the reference plane is the same. As long as it is same, things are fine. So the probability remains the same in terms of classical randomness. Okay. And what happens after observation classically? So classically, you toss a coin. Until the coin lies on the ground, you do not know whether it is heads or tails. So we introduce probability. Once you see the coin, once the coin is known, once the result of the coin is known, then the result becomes deterministic. Okay, once the coin is in the ground and someone sees it, then clearly they can say it is heads and tails. After that, it is not going to change. It is either heads or tails on whatever the observer sees. So to model this in this coin toss perspective, in this observation reference plane perspective, so what we will do is when someone sees a coin, he will push the coin to the floor along the same lines. So for example, in this case, if the someone sees from the yellow side, after seeing it, he will push the coin on the floor on the reference plane with the yellow side, so that anyone who sees after him will see yellow. He won't see anything else. Okay, and similarly, you can think about someone towards the reference plane, facing the green face facing the observation sphere, which means after that anyone who sees the coin, he will see it as green. It will not change. Okay. Now I wanted to introduce qubit. Now so far we have classical qubit, random qubit, and so on. Sorry, classical bit and random bit. Now we have to introduce quantum bit. So a slight difference between classical bit and quantum bit in terms of this observation reference plane picture is the in quantum the quantum bit, the reference plane is also allowed to be changed. So you can change the reference plane also along with this. Though here red is, I have marked red as such, but we are changing the observation sphere and the reference plane together. Okay. So the both the planes are changed. So for example, in this case, if the coin is like this, now if my observation sphere is like this, then I can see green with certain probability, which is less than 0.5, and yellow with certain probability, which is greater than 0.5. But if I tilt the observation sphere a little bit, then I can see green with higher probability and yellow with lesser probability. And again, I can tilt the sphere, observation sphere to some angle over which you can always see yellow. You will not see green at all. So in this case, always you can see a yellow. Okay, so you can tilt accordingly. So which means the distribution changes with respect to reference plane. And now in this case, if you see earlier in classical sense, these three coins gives the same distribution. But now in this case, in one observation sphere, they give the same distribution. That is the classical observation sphere. But if you change the observation sphere, if you tilt the observation sphere, the distribution changes. So that is the idea. And to model this kind of distribution changes, what we will do is we will bring in this vector notation. And classically, this is the case. We have the notation of alpha and beta. Earlier, we have talked about root p and root of 1 minus p. This vector, that's exactly this one, where alpha equal to root p and beta equal to root of 1 minus p. And classical senses, it is alpha and beta, where alpha and beta are positive numbers, satisfying magnitude of alpha square plus magnitude of beta square equal to 1. And once you measure it, you will get bit 0 with the probability of magnitude of alpha square and 1 with the probability magnitude of beta square, depending on the measurement outcome. And once it is measured, then it is fixed with 0 or 1. So this corresponds to 0, this corresponds to 1. Okay. depending on the measurement outcome. So this is what the classical randomness is. And a slight tweak of that is quantum state, where you have alpha and beta, and this alpha comma beta takes values from complex numbers. That is the only difference that comes up here. Okay. Remaining theories remains the same. Like, you do post measurement, you get zero with probability magnitude of alpha square, and one with probability magnitude of beta square. Okay. And these are some interesting states which are quantum states, which we call it as plus state and minus state. And these are some other interesting states. So we don't use this much, but still at certain theories it will be used. So we are not going to talk about it. And so this is what quantum information is. So your coin can be tilted, and you can you can rotate the observation sphere and the reference plane along together, joint. Okay. And next thing is you have to see how the major operations can be done. So in classical sense, the coin lies on the ground. So in classical sense, it will be like this. So you flip the coin. There's only one operation. You flip the coin on upside down, or that is, you flip the coin along with the xy plane. So you can call this as x, y, and z plane. So you flip the coin along xy plane in classical sense. And in quantum sense, we have it's a three-dimensional axis, so we have flipping on many directions. So in xy plane, which we call it as p operator, and in flipping in zy plane, which we call it as x operator, and switching in zx plane, which we call it as y operator. And these are called as Pauli operator. In matrix form, these are denoted by these things. So identity is not switching, not doing anything, keeping it ideal. And these operators are called Pauli operators. And if you see, this X is classical display here. And there are a few other major operations which are called as rotation operators and control knot operators. And rotation operator is like you are three dimensions, so you have to rotate the coin accordingly. And control knot operation is like you have two qubits. Now it's like think about exclusive OR gate. Now you have a x gate, x coming in, y coming in, a quantum vector y coming in, and now you wanted to perform exclusive OR. Here you get exclusive OR, and here the x remains as such. To maintain the invertibility of the quantum system, so we will keep this node also, this qubit also as such. This will represent at least. But later on, there are algorithms which separate this out. In classical sense, this is represented by a exclusive OR gate. This is a exclusive OR gate. But then here you have two input and one output. In this case, you have both two input and two output. Okay. And the interesting is we can just like classically using the NAND gate, you can develop any quantum gates. In quantum sense, you can using this Pauli operators, rotation gate, and this control knot gate, you can represent any quantum operation. Not okay. And the last thing is measurement. I have told you. So measuring the qubit twice yields the same result, which means the first person has pushed the coin along that reference plane. So the first someone from the green side, they might have seen this coin. So they have seen the coin green. So they push the coin along the reference plane. So everyone who sees the coin after that will see it as green. Okay. And interesting thing is, if the second person who wanted to see the coin, if they change their plane, if they change their reference plane to some other direction, then again randomness comes back. Okay, so it is deterministic in one plane, but it will become random in another plane. And measurement mathematically it is modeled by some operator, so I am going to skip this part. Okay. And in textbook literature, this kind of things will not be explained much. But then there is something called a block sphere in textbook. So, for example, suppose a coin is like this, then the exact block sphere point for this is you draw a sphere here, and you draw a tangential lines for this, a perpendicular lines for this this plane, the plane over which the coin is there. So you draw this line, and along the heads, one part, heads are tail. Here we choose greens. So it hits the sphere at one point. So that is how they represent it in block sphere representation. Okay. So this is what the point xi represents. If the angle is like this, then your state will look something like. And these are some interesting points in blocks here. Ket 0, ket 1, and these are the interesting states. So plus and minus will be pointed here, and so on. Okay. And the last thing that to be highlighted is how a multi-qubit is represented. So how can you represent two qubits, for example? One qubit we understood. Okay. So it is like alpha times 0 plus beta times 1 is 1 qubit, where magnitude of alpha square plus magnitude of beta square equal to, sorry, beta square equal to 1, and 0 will be equal to 1 0 this vector, and 1 will be equal to 0 1 this vector. So okay, 1 bit you understood. And 2 qubit, what we will do? Like 2 qubit again, it's the same notion. Now we need 4 1 0 and 1 1. So an arbitrary state will have superposition of 0 0 1 0 1 1 0 and 1 1. So an arbitrary state will look something like this. And mathematically, this can be denoted as something called as tensor product. That's what I have written here in this part. So which we can skip for now. But if you are interested, you can go back and see what tensor product is. For now, you can understand that 0 0 represents the first point, 0 1 represents the second point of the vector, 1 0 third point, and 1 1 fourth point. The coefficient corresponding to 1 1 corresponds to the fourth point of. Okay. And the next thing, why should you see, why you should learn why quantum is being hyped? Because of three main reasons. One property is no cloning, second is superposition, and third is entanglement. The idea of no cloning is you cannot copy the quantum state. So suppose you can copy a quantum state, it violates linear operator. So all these quantum operations that we have discussed here, all are linear operators. Suppose we assume a quantum bit can be copied, a pure quantum bit can be copied, then the problem is the linearity property gets violated. That's what we can describe here. Suppose there is a unitary operator U that copies state from the first qubit to the second qubit, then it will not satisfy the linearity. So you can cross check it. Okay. So the idea is you cannot copy a quantum bit. So what we can do? So we try to sorry.